So, today we will discuss real crystal system or real crystal structure. So, as I mentioned earlier that basically lattice plus basis that gives the real crystal structure. So far we have mainly discussed about the lattice, Bravais lattice. As we have seen this, there are 14 Bravais lattice. So, out of this 14 Bravais lattice, 9 Bravais lattice, 9 Bravais lattice have orthogonal axis, crystal axis ABC, where alpha equal to beta equal to gamma equal to 90 degree. So, basically this cubic crystal system, cubic crystal system which has 3 simple cubic, body centered cubic and face centered cubic, right. And then we have tetragonal, it has 2 type, one is simple tetragonal and another is body centered tetragonal. So, simple and body centered. Right. So, for cubic basically A equal to B equal to C, and for tetragonal A equal to B is not equal to C, right. And another orthorhombic axis system, that orthorhombic crystal system having orthogonal axis, orthorhombic crystal system. So, it has 4 Bravais lattice, it is simple, then body centered, then face centered and base centered So, this for here A is not equal to B is not equal to C. Okay. So, all angles are 90 degree, but there is a variation of this ABC. So, so total is basically 3 to 5, 5 and 4, 9, total 9. Out of 14, total 9 are having the orthogonal axis system, and other this we have other crystal system, this say hexagonal, So, in this case basically two angle are 90 degree, two angle are 90 degree, alpha beta equal to 90 degree, but gamma is not 90 degree, it is 120 degree, right. And we have monoclinic, it has also two angle are 90 degree, one angle is not 90 degree. So, this alpha equal to gamma equal to sorry, it is not 0, it is 90 degree. So, it is 90 degree, but beta is not equal to 90 degree. So, it is not even 120, so it can take any value other than the 90 degree. Okay. So, in case of hexagonal, A equal to B is not equal to C, right, and in case of monoclinic, A is not equal to B is not equal to C. So, then we have two more, that is trigonal. We have two more, this trigonal and trigonal and triclinic, right, trigonal and triclinic. So, in both cases, so in case of trigonal, all angles are different than 90 degree and their ABC also different, but in case of that is for triclinic, it is for triclinic, A is not equal to B is not equal to C, and angle are different, alpha is not equal to beta is not equal to gamma, okay. And for triclinic, or it is called rhombohedral also. So, in this case A equal to B equal to C, but this all angle are different, and they are not 90 degree. Okay. So, these are the so from the here 9 and from here one can get basically 5. Okay. So, only so this for this trigonal and triclinic is only simple type, and in case of hexagonal also it is only simple type, but monoclinic have simple and base centered, these two are there, simple and base centered. So, basically this is simple 1, this is monoclinic simple and base centered 2, so 3, and this is simple 3 4, and this is simple 5. So, total 5 plus 9 is 14 Bravais lattice. Okay. So, just we have discussed them, and so for what we wish to find out now, the real crystal structure of a material. So, as we have discussed that material will have crystal structures taking one of the Bravais lattice out of 14, it will have one lattice, one type of lattice, and then adding basis in that material one can find out the real crystal structure of that material. So, same Bravais lattice, but adding different basis in that structure in that lattice, we can get real lattice structure of that material. So, let us take some materials which are familiar to us. So, what are the materials generally we see frequently in our day to day life? So, that is gold, silver, platinum, right. So, this generally people use for ornament, and other material say copper, aluminum, etc. So, these are basically metal. These are metal, and all of them are having FCC structure, FCC lattice, Bravais lattice is FCC. Now, in this FCC, if you use just gold atom, then it will be gold. If you use copper, it will be copper. Okay. So, where we will put this? Where we will put this atom? So, if it is purely FCC, and this atom can be put at the corner of the unit cell, or at each lattice point directly you can put the gold atom. Okay. So, that will be FCC structure. Similarly, if you use copper atom at each lattice point, so it will be copper material. So, having the FCC structure. Okay. So, there are other materials. If I list them, say carbon, silicon, germanium, right. So, these are the materials generally we do not see except carbon, carbon we see, yeah. So, it has different form, graphite, diamond, different forms. So, carbon is diamond form. Okay. So, again all these material, as I told, these are basically metal, and these are basically semiconductor. So, carbon in diamond form is not semiconductor. So, rather than carbon, so you can, this silicon germanium is basically semiconductor. Okay. So, again all these three materials, again they are having the FCC structure. So, it has Bravais lattice, this FCC type, right. So, but this is the metallic and this is the semiconductor, and but they both are having the same FCC structure. So, what are the difference? So, here I told these atoms will sit at the lattice point, but in this case it is not it is slightly different. So, it is different, that basis type is different, as these are different atom, but main difference structure wise comes from the basically how bases are arranged, in the lattice. Okay. So, main structure is FCC. So, that is Bravais lattice, that is there. Now, now that although all are having FCC, but for different material it has different property, different property, okay, electrical property, this magnetic property, etc. So, they are different, although their structure are same. So, this because of the distribution of the bases in that FCC lattice. So, that decide the properties of those material. So, let me tell some more material like sodium chloride, potassium chloride, okay. Then your cesium chloride, then zinc sulphate. Okay. So, these are here just we have seen this pure made of pure atom, okay, but here this combination of atom. So, they are having also these two are having this again FCC structures. These are having I think simple cubic, and these are having zinc sulphide. These are having FCC, okay. So, so what we are seeing here, that many materials are, most of the materials are having here, whatever I have cited are having the FCC structure, okay. But they are different material. So, they are different material, it is not only for the different bases, it is also very important, and it is this main fact is that the bases, how bases are distributed in that structure, in FCC structure, that is the important factor which decide the properties of the crystal. So, so this structure, this you see this gold, silver, this your silicon, germanium. So, they are having the same structure, FCC structure, but as I told that bases are distributed in the in that structure in different ways, okay. And how they in same lattice, but why these atoms are arranged in different way. Their bases are arranged in this material, in this structure in different way. So, that is basically because of the bonding, So, this in this case, this metallic bonding is responsible for such type of crystal. Metallic bonding is metallic bond, okay. And for this type of material, the sodium chloride, potassium chloride, so this cesium chloride. So, here basically ionic type of bonding, ionic bond, okay. And for this diamond, silicon, germanium. So, here this covalent bonding is responsible, covalent bond is responsible for this type of structure. So, same FCC, but different structure based on the distribution of the bases. So, that is because of the different bonding among these atoms in solids. So, I will discuss this different kind of bonding. These three are the primary bonding, but there are two more bonding. So, I will discuss about this bonding, crystal bonding in another class, but now what I want to continue, that what about the structure of real crystal. So, this FCC structure, and these atoms are just sitting at the lattice point, that is fine. Apart from that, there are very famous and convenient structure, generally we call them in different name. So, that I will discuss. So, one is this called sodium chloride structure, sodium chloride structure. So, this is the special name. It does not mean that it is only for sodium chloride, but in sodium chloride structure, the way the bases are distributed, there are some other materials, they follow the same structure, they follow the same distribution of the bases. Okay. So, the materials which are following the same distribution of the basis of this as the sodium chloride. So, we call them this sodium chloride structure. So, that material follows the sodium chloride structure. So, basically potassium bromide, magnesium oxide, and this silver bromide. Okay. So, they are also having the same structure of sodium chloride. So, that is why when we tell this magnesium oxide follows the sodium chloride structure. So, now this is not for only sodium chloride, but this is now a common structure of some material. So, this is the sodium chloride structure. So, I can draw it, but I can show in model. I think so. This is the sodium chloride structure. Here you can see that this is the cubic structure, FCC structure, FCC lattice. As I told that mentioned that sodium chloride is having FCC Bravais lattice. So, FCC Bravais lattice means it is the cubic structure. So, this is the cubic structure as a whole, this is the cubic structure, right. And so, how many corners are there? 8 corners are there, 8 corners are there, 8 corners are there, right. And in each face 6 faces are there, in each face. So, lattice point will be there. So, whatever brown color we are seeing, that if you just look at the brown color, then that is the you can see there is a FCC lattice, right. Now, sodium chloride, now basis is sodium chloride, right. So, we have to put in this lattice, we have to put sodium as well as chlorine, right. So, how to put them? So, now if you just consider that okay, each lattice point, in each lattice point if we put the chlorine, so brown color chlorine, then we can add sodium, this whatever the white color you are seeing, white ball, so that you can take as a sodium position. So, here also you can see that sodium just it is between two chlorine, 1 sodium, between 2 chlorine, 1 sodium. Okay. So, here this here basically one can also tell that this, if you just consider the white one, then you can see that this also can be treated as a FCC. Okay. So, here what you are seeing, here just brown one, if I see just 5 brown and then middle 4 brown and then again 5 brown. So, if you just look at the white one, so this is here 5 white, then 4 white, then again if you consider the next one, so again 5 white will come. So, as if two FCC lattice are intercept are basically what is called inter positioning in this same structure, just shifting one from the other by half, just shifting one from the other by half. Okay. So, that way this is the sodium chloride structure. So, in sodium chloride structure we have the FCC, and at lattice point if I consider the chlorine or sodium, anyone you can consider, and then other one either sodium or chlorine, it will be placed following this another FCC. So, as if the just two are placed just shifting by half of the lattice. Okay. So, that way this the one can realize the sodium chloride structure, and other metals also have the similar structure. In case of potassium bromide, sodium will be replaced by potassium, bromine will be replaced by or chlorine will be replaced by bromine. Magnesium oxide, in case of magnesium, magnesium can sit at sodium place and oxygen can sit at the chlorine place. So, we will get the magnesium. So, basically for all this material, the distribution of bases is placed in such a way, this for all of them they will have the same position. Okay. So, one can in principle find out the coordinate, basis coordinate, where the base, where these bases are placed. So, so from the structure itself I can tell. So, in FCC lattice, how many lattice point per unit cell? Basically 4 lattice point per unit cell, right. So, from 8 corners, so contribution is 1/8, right. So, 1, and from 6 faces are there. So, from each face this contribution is half, right, is shared with 2 cube. So, half. So, from 6 you will get 3 plus 1, that is basically 4. So, so 4 lattice point, okay, per unit cell. So, in principle there should be 4 sodium chloride, because in basis is attached with each lattice point in same way. So, that is the condition for real crystal structure, arbitrarily you cannot put. Okay. So, in that case you should have 4 sodium chloride per unit cell. So, in principle there are 4 sodium chloride. So, here if I just I can take this is in middle, if I take this is the sodium. Okay. So, this sodium I can take this origin. So, this coordinate of this one will be 0 0 0, right. So, then from sodium So, this another. So, if you consider this, so I need 4, right. So, choosing the axis here. So, if I go this next sodium, I will get half, half, 0. Then I can get this one half, 0, half. Then I can get this one for that this 0, half, half. Okay. So, these 4 coordinate for the sodium, and so you can see here. So, there are 4 chlorine also attached with this each sodium. So, this coordinate of this one will be half, 0, 0, this one 0, 0, half, this one half, 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 and other one will be basically 0, half, 0. Okay. So, what are the coordinates I got for these 4 bases for sodium ion, basically ionic crystal chlorine ion. So, as I told, this middle one, if I take 0, 0, 0, okay, and then other 0, 0, 0. So, then other one I can see from here half, 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 0. Then from the structure I am seeing, as I already described you, half, then I can see half, 0, half, then I can see 0, half, half, 0, half, half, right. So, corresponding. So, here interesting things is that the basis. So, whether I will take basis, whether I will take basis of this on this or other one. So, actually basis is just the distance between the this sodium and chlorine as a basis is just basically half of the body diagonal. So, this will be the for this will be the chlorine, for this will be the chlorine. Okay. So, for this will be the chlorine, for this will be the chlorine. Okay. So, so if 0, 0, 0 for this sodium, so chlorine, as I told, is just half diagonally, its body diagonally is half distance. So, body diagonally is half distance, right. So, what will be the coordinate of this one? So, this coordinate is 1, 1, 1, right. So, this coordinate is 1, 1, 1, coordinate is 1, 1, 1. So, these two is basically forming one basis, these two is one is forming a basis, and then if you take this one. So, this is half, 0, half, half, 0, half, right. So, basis is, so corresponding chlorine will be this one. So, this again this half of the body diagonal. So, this what is the coordinate of this one? This 0, 0, sorry 0, half, 0. So, for half, 0, half, I am getting 0, half, 0, right. So, where half was there, in that case it is coming 0. So, this basically half, 0, half. So, 0, half, 0, right. So, just all will follow this way. So, just blindly I can write this way, just blindly I can write this way, okay. And you can find out this according to the way I showed you. Okay. So, these are the 4 bases, these are the 4 bases, sodium chloride bases in that structure, sodium chloride structure. Okay. So, and this, and as you know this, we have to attach the basis to each lattice point in same way. So, distance between the sodium and chlorine, it cannot be different for this different 4 bases, right. So, here whatever the distance between this sodium chloride, in all cases you can see this it is the distance of the basis is just half of the body diagonal of this cubic. Okay. So, this is the sodium chloride structure. So, we will discuss some other structure in next class, interesting structure. So, I will stop here. Thank you.